we're going to see uh, a system with a transfer function and what the transfer function poles and zeros do in this response of the system. So the lecture today we could call it the effect of poles and zeros in systems response. So let's take a look at this simple example that you see on your screen. And here's what we have. We have this transfer function, which is the system itself. And it says the numerator has s plus 2 and the denominator is s plus 5. Okay? So the input to this, you see that input 1 over s is a test signal that we can use for doing this. Okay, so the question is, what is the response C of S? This response here once we know this input. All right. If we make a plot on the complex plane, we realize that if you solve the numerator, if you say s plus 2 is equal to 0, then s is equal to minus 2. So we can plot in here. You see there's the 0 for the numerator. And if you put s plus 5 equals 0, you get a root for the denominator, which is minus 5. All right. So in here we have the situation that we have this input, this if you put the input, if you, s is equal to 0, then we have 1 0 right here, one pole right here. We have this 0 here, and then we have this pole. So you see all three of these are on the real axis. But the type of response that we get from this plus this would be something like this. This is the way the output would look like. So it is a combination of a constant term plus a exponential decay. That's what the response would be. So if you have a pole that is on this side in here, this generates a response of the type e to the minus e alpha t, which is like, let's see if we can draw it over here. That kind of a response is like this. See, this is the form that we are saying is k e to the minus alpha t, like that. So what would happen if the response is what would happen to the response if the pole, instead of being here, would be over here, and they have like complex conjugates, right? So if it is in here, the response of this would be not just an exponential decay, but it would go like a combination of an oscillation plus the decay. See, this is it would be the combination of these two. So this would be the response when the pole is, for a pole, let's say that is this is has an imaginary part and it has a real part. Yeah. Okay. If you have a first order system, let's say, of this type, just simple like this. So you have minus a pole over here. Like I said, our response to this would be simply a decay. This would be like this, yeah. See, what is important is when you when you when you do an input response to a system, it will just produce this kind of curve where this is one, which is the input one, let's say. It raises from 0 to that, no oscillations for this kind of system. And here we can classify the parts of the response in here with this so-called time constant. So we divide this in these values based on the initial slope. The inverse of the initial slope would be 1 over the time constant. So you would say in this case it takes 4 of these time constants to get to a steady state value, and after that there's no more response. So I think it would be helpful if we can try this simple system in MATLAB. Let's just do that. So I have MATLAB running over here, and I am going to describe the transfer function. And the way I'm going to do that is by entering the numerator and the denominator. But before that, let's make this a little bit more visible. So this is going to be like this, and let's do that. Okay? Yeah, then you can see it really well. So I'm going to say the numerator of the transfer function, you could say, we say a constant, let's say like 3. Yeah? And so that's that. The denominator of the transfer function is going to be s. The denominator will be s plus 5. Okay, so the coefficient of the variable s is 1, and then the constant term is 5. And by entering the coefficients, we are describing a polynomial to MATLAB. So we're going to define the transfer function g as being the transfer function between the numerator and the denominator. See, that's what it means. And if we do this, this is what we have. So you see, we have the transfer function 3 divided by s plus 5. So if we do this, we could do the test with this transfer function. Test using the step like that, and we should get the response that we predicted, exactly like we had it on the slide. You see, here like this. See, so we are going to be changing the transfer function and comparing it to the response of the system. So let's go ahead and study this a little bit more in such a way that with different transfer functions we get different results. So let's go to my slide over here, and let's go back to full screen. So if we go over here, this is what you just saw, the step response to the system. Now, one thing that you would notice here is that the amplitude of this in this example does not quite get to 1. Yeah, and that is because in this case we have what is called a steady state error. So you see, that's what we have also over here. Yeah. So the first indication of this is that there are certain transfer functions that do not allow the system to get to 1 here, but rather it has a steady state error. Those are the kind of things that we need to talk about a little later, and how we're going to correct those. But in the meantime, what I would like to do is to show you what would happen if you have these systems here, different kinds of systems. And here you have this system that has the poles on the real axis, and of course it has to because it is a quadratic equation. See, but you see the author of your book does a wonderful job to demonstrate for you what would happen if instead of being on the real axis they are on the imaginary axis, or if instead of being on the imaginary, instead of having a component the real plus an imaginary, they only have imaginary ones. What will happen? Or if you have one that has this critically damped system, I think it would be a good idea to try this. Okay, I'm also going to show you another way to input the transfer functions onto MATLAB. So let's let's keep this over here, and then I may have to go a little bigger so that we can actually see it. Yeah. All right. There we go. So we are going to enter this transfer function over here. So I'm going to show you something really neat. I am going to clear everything that I did, and so I don't have any values on the workspace, no definitions in here. So I'm going to make a definition that the variable s is of type transfer function, like that. Okay, so it says continuous transfer function, the variable s. So I am going to describe this transfer function to the computer, and I would like to do it just entering as if I were writing it on paper. So I say divide 9 by, I like parentheses, so to make sure that we don't mess up, we're going to say s, and then we put in here the s squared like this, yeah? And then we say plus 9 plus 9s. You have to put the 9 times this. In other words, the computer doesn't understand this. So then you have plus 9. Okay? And if you do this, you are going to find that the transfer function g in this case is equal to this. Okay? When I click return, the computer is going to produce the transfer function exactly like it's in here. See? So in here now, we're going to do a step input on this. And let's see if we can get the the answer that we expect, like on the back in here. So in here we're gonna say step. I don't think we have a plot, do we? Let's just erase this so that we get a new one. So I'm gonna say step of the transfer function g like that, and see what we get. See? This is the response that we get. This one doesn't have stay there. Okay? And if we change, you see, what's the difference between this and this? What has happened is we changed the damping coefficient in here and caused that the denominator has imaginary roots. See? So in here, this is it's important to learn to use MATLAB in here the way we have done it in the past here. This was the 9, right? And now what we would like to do is to make this into a 2. Yeah? And if you do that, you're gonna get the transfer function like it's in here. And if we actually do the transfer step input of this transfer function, see what we got? Okay. I think the message that I'm trying to give you, and I hope it is coming clear now. By tweaking those coefficients of the denominator, we can actually change the way the system responds. This is the central message here. Central message is that if we change the coefficients of the denominator, we can actually, it makes a difference because the poles move to either from the real axis to the real and imaginary components, and when you do that, you have this kind of response here. This would be like an overshoot in here, and it would dump out to the point that our step input of 1 would get we will get that kind of a response. Let's test this other one in here. This one doesn't have the middle term, so one thing we could do to test this would be to say, okay, on this, if I put this as 0 or I just disappear, we could just do it like this, not to change so much, and you get the transfer function. Do you see this is the transfer function here, this one? So if we do that and we go again and say a step, I'm just using the up arrow, you bring back the commands that you typed previously, and I can run what I need. This, of course, seeing so many oscillations that the other one was just a few seconds, but this is like 450. But yeah, that's what you're seeing here. We see that the response of this one would be an oscillation forever. So here are the conclusions that I would like you to take from this discussion. 1, if you have a transfer function like this, where the poles are only on the real axis, you're not going to get oscillations. If you modify this and then the poles have real and imaginary components, you will get a damped system that has a bit of an overshoot and then it damps out. And if you have imaginary axis in here, you have this axis that where s is plus or minus square root of 3 or square root of minus 3, you're going to get only oscillations. This is by tweaking the number and putting this as 6, we have an and we have a critically damped system, and I think it would be a good idea to also try that, as we are trying the the different possibilities here in MATLAB. Let's see, let's try to erase the figure so that we get this, and you see what, here's where we are, right? Instead of a 0, this is a 6. And when you type that, you get the transfer function that we had with the 6 in there. And if you go and do the step input in here, you're going to get this critically damped system. No oscillations, just a response like that. So the conclusion is, by changing the location of the pulse, we change the response.